Welcome back to the channel. Today we're diving deep into one of the most revolutionary breakthroughs in deep learning, the attention mechanism. If you ever wondered how ChatGPT, GPT-4, or Google Translate work so well, you're about to find out. The attention mechanism didn't just improve existing models, it completely transformed how we think about processing sequential data. Before attention, we had this fundamental problem. How do you make a neural network remember important information from the beginning of a long sentence when it's processing the end? The key insight that changed everything was simple but profound. Instead of trying to compress all information into a single vector, why not let the model look at all parts of the input simultaneously and decide what's most relevant? This is the story of how attention went from a clever trick to the backbone of modern AI. Let's get started. Before we understand the solution, we need to understand the problem. Let's go back to 2015, when RNNs and LSTMs were the state of the art for sequence processing. Look at this architecture on the right. See how information flows sequentially? The word the gets processed first, then cat, then sat, and so on. Each step depends on the previous one. Here's the first major issue, the information bottleneck. By the time we get to the word mat, most of the information about the has been diluted through multiple processing steps. It's like a game of telephone. The message gets weaker with each step. Second problem, vanishing gradients. When we try to train these networks, the gradients that help the model learn become exponentially smaller as they travel back through time. This means the model struggles to learn long-range dependencies. And third, no parallelization. See those arrows? Each step must wait for the previous one to complete. This makes training incredibly slow, especially for long sequences. The formula you see here, ht equals f of ht minus 1 and xt, perfectly captures the problem. Each hidden state depends on the previous one, creating this sequential bottleneck. Imagine trying to understand a book by only remembering the last sentence you read. That's essentially what RNNs were doing with long sequences. Now here's where it gets exciting. The attention mechanism solved this with a beautifully simple idea. What if we don't compress everything into a single vector? What if we let the model look at all input tokens simultaneously and decide what's most relevant? This is the core breakthrough. Direct access to all information. Instead of information flowing sequentially and getting diluted, every position in the sequence can directly access every other position. Let me show you this in action. Try clicking on different tokens in this demo. See how each token can attend to different parts of the input with different weights? The model is literally deciding, for this current token, which other tokens are most relevant. This is completely different from RNNs. If you click on cat, the model might pay attention to sat because there's a subject-verb relationship. If you click on mat, it might attend to on because of the spatial relationship. The attention weights you see below, these numbers sum to 1 and represent how much the model cares about each input token when processing the current one. This is learned during training, not hard-coded by us. This direct access means no more information bottleneck, no more vanishing gradients for long-range dependencies, and, as we'll see, the ability to parallelize computation. Let's break down exactly how attention works. There are 3 key components, and I like to think of them in terms of a database analogy. First, we have query. Think of this as your search term. It represents, what am I looking for? If you're processing the word sat, the query might be looking for subjects or objects related to the action. Second, key. These are like the index labels in a database. They represent what information is available. Each position in the sequence has a key that describes what kind of information it contains. Third, value. This is the actual information content, like the data stored in your database. Now, here's the mathematical magic. The attention formula might look intimidating, but it's actually quite intuitive. Attention of Q, K,
V is equal to softmax of Q K transpose divided by the square root of D sub K times V. Let me break this down step by step. First, we compute QK transpose. This is the dot product between queries and keys. High dot product means high similarity. We divide by the square root of the key dimension for stability, then apply softmax. This ensures our attention weights sum to 1. They form a proper probability distribution. Finally, we multiply by V to get the weighted sum of values. The database analogy really helps here. You submit a query, the system finds the most relevant keys, and returns the corresponding values. The attention weights tell you how relevant each piece of information is to your current query. Let's walk through the attention computation step by step. This is where the magic happens. Step 1. Create Q, K, V matrices. We start with our input embeddings. These represent our tokens in vector form. We then apply 3 different linear transformations using learned weight matrices, WQ, WK, and WV. This creates our query, key, and value matrices. Step 2. Calculate attention scores. We compute the dot product between queries and keys. This gives us a score matrix where each element represents how much attention position I should pay to position J. Step 3. Scale and normalize. We divide by the square root of the key dimension for stability, then apply softmax. This ensures our attention weights sum to 1. They form a proper probability distribution. Step 4. Apply attention. Finally, we multiply our attention weights by the value matrix. This gives us the final output, a weighted combination of all input information. Each of these steps is differentiable, which means we can train the entire mechanism end-to-end using backpropagation. The model learns what to attend to based on the task at hand. Now let's play with attention ourselves. This interactive demo lets you see attention in action with your own sentences. I've preloaded the quick brown fox jumps. Let's analyze this. The model is currently focusing on the word fox. Notice how it pays different amounts of attention to other words? The attention weights show us that when processing fox, the model pays moderate attention to quick and brown. These are descriptive words that modify fox. It pays less attention to the and jumps because they're less directly related to understanding what kind of fox we're talking about. This is exactly what we want. The model has learned to focus on semantically related words. Feel free to type in your own sentences and see how attention patterns change. Try something like, the cat chased the mouse. You'll see the model creates different attention patterns based on the relationships between words. Now here's where attention gets really powerful. Multi-head attention. The idea is simple. Why have just one attention mechanism when you can have multiple ones running in parallel? Think about how humans process language. When you read a sentence, you're simultaneously paying attention to syntactic relationships, subject, verb, object, semantic relationships, what words mean together, positional relationships, word order, and contextual clues. Multi-head attention captures this by having different heads specialize in different types of relationships. Look at the example. Head 1 focuses on syntactic relations. It's paying attention to the subject-verb relationship between cat and sat. Head 2 focuses on semantic relations. It's connecting cat, sat, and mat because they form a coherent action-object relationship. The mathematical formulation shows we run multiple attention computations in parallel, each with their own learned parameters, then concatenate the results. This gives the model much richer representations. In practice, different heads in models like GPT or BERT have been shown to learn different linguistic patterns. Some focus on syntax, others on co-reference, others on semantic similarity. It's like having multiple specialists working together on the same problem. Let's talk about self-attention. This is when the input sequence attends to itself. This might sound circular, but it's actually incredibly powerful. In self-attention, each position in the sequence can attend to every other position, including itself. This allows the model to build rich representations where each word understands its context within the entire sequence. Look at this attention matrix. It's like a heat map of relationships. Each row shows what a particular word attends to. For example, when processing cat, the model strongly attends to sat, the verb, and moderately to the determiner, and mat, the object. This is fundamentally different from traditional approaches. In an RNN, cat only has direct access to the previous word. Here, cat can directly attend to mat at the end of the sentence, even though they're far apart. Self-attention is what enables models to capture long-range dependencies effectively. A word at the beginning of a paragraph can directly influence the processing of a word at the end with no degradation of information. This is why transformers work so well for tasks requiring understanding of context and relationships across long sequences. Now let's see how attention fits into the bigger picture, the transformer architecture. This is the attention is all you need paper architecture that started it all. The key insight was revolutionary. We don't need RNNs or CNNs at all, just attention and feed-forward networks. Looking at the encoder stack, we have multi-head self-attention, allows each position to attend to all positions in the input. Feed-forward network processes each position independently. Residual connections and layer normalization helps with training stability. The decoder adds one crucial component, masked self-attention. This ensures that when generating text, the model can't peek at future tokens. It can only attend to tokens that come before the current position. There's also encoder-decoder attention, where the decoder attends to the encoder's output. This is crucial for tasks like translation, where you need to align source and target sequences. The beauty of this architecture is its simplicity and effectiveness. No complex recurrent structures, no convolutions, just attention, feed-forward layers, and some normalization. Yet, it achieves state-of-the-art results across numerous tasks. This architecture scaled from the original transformer with 65 million parameters to GPT-4 with 175 billion, showing its incredible flexibility. Here's a subtle but crucial detail. Attention is permutation invariant. This means the cat sat and cat the sat would be processed identically. The model has no inherent understanding of word order. This is obviously a problem for language where order matters enormously. The solution is positional encoding. We add position information directly to the input embeddings. The original transformer used sinusoidal positional encodings with this clever formula. Don't worry about memorizing it. The key insight is that it creates unique, smooth encodings for each position. Why sinusoidal functions? They have several beautiful properties. Each position gets a unique encoding. The encodings are smooth. Nearby positions have similar encodings. The model can potentially generalize to longer sequences than it saw during training. The patterns are regular enough for the model to learn relative positions. You can see the visualization here. Each word embedding gets combined with its positional encoding. This gives the model both semantic information, what the word means, and positional information, where it appears in the sequence. Modern models like GPT use learned positional embeddings instead of sinusoidal ones, but the principle is the same. We need to explicitly inject position information into an otherwise position-agnostic mechanism. Let's talk about impact. The attention mechanism didn't just improve academic benchmarks, it transformed entire industries. In natural language processing, attention enabled GPT models, from GPT-1 to GPT-4 and ChatGPT. BERT revolutionized language understanding, now used in Google Search. Translation systems. Google Translate's quality jumped dramatically when they switched to attention-based models. But attention went beyond NLP. Computer vision saw vision transformers, or VITs, challenge CNN dominance. Audio processing benefits from attention in speech recognition and music generation. Even protein folding. AlphaFold uses attention to understand amino acid relationships. Look at these impact statistics. The Transformer paper was published in 2017, and by now about 95% of top-performing NLP models use attention. We've gone from models with millions of parameters to hundreds of billions. The attention mechanism fundamentally changed how we think about sequence modeling. Instead of trying to compress information into fixed-size representations, we let models dynamically focus on relevant information. This has enabled the current AI revolution, from ChatGPT to GitHub Copilot to DALL-E. Attention is the secret sauce that makes it all work. Let's wrap up with the key takeaways from our deep dive into attention mechanisms. The core mechanism is beautifully simple: query, key, and value components that let models dynamically focus on relevant information. The attention weights come from softmax normalization, and everything is learned end-to-end. The architecture innovations include multi-head attention for capturing different types of relationships, self-attention for rich contextual representations, and positional encoding to handle sequence order. The advantages are clear: parallel processing instead of sequential bottlenecks, direct modeling of long-range dependencies, interpretable attention weights, and incredible flexibility across domains. The limitations are real but manageable: quadratic computational complexity, significant memory requirements, and the need for large datasets. But these are being actively addressed with techniques like sparse attention and efficient transformers. Remember this formula: attention of Q, K, and V equals soft max of Q, KT times root of DK times V. This simple equation changed the course of AI research and enabled the current generation of large language models. The attention mechanism is more than just a technical innovation. It's a new way of thinking about how machines can process and understand information. Instead of rigid sequential processing, we now have flexible, dynamic focus that more closely mirrors human cognition. Call to action: if you found this explanation helpful, please like and subscribe for more deep dives into AI concepts. What would you like to see explained next? Drop your suggestions in the comments below. And if you're working on attention-based models or have questions about implementation, let's discuss in the comments. The AI community thrives on sharing knowledge and helping each other learn. Thanks for watching, and I'll see you in the next video.